Continuing dealing with open systems, in the last video, we applied a control volume analysis to conservation of mass. Today, we will do a similar analysis, but now for the first law of thermodynamics, conservation of energy. In an open system, mass can flow in and out. This matter has some amount of inherent energy inside it, and so this will change the amount of energy inside the control volume since it brings this energy along with it. This is in addition to other changes that may be occurring, such as heat or work. Another way of looking at this is that it generally is going to take some work to push the fluid into or out of the control volume. This is called flow work or flow energy. This is denoted by W flow and is equal to P times V, the pressure times volume. We saw previously that the total energy in a substance is the internal, kinetic, and potential energies all added together. E equals U plus KE plus PE on a per unit mass basis, as written here. For open systems, we need to add in the flow energy that we just saw as well. To distinguish these energies, the total energy for open systems is denoted by theta. So theta equals E plus P times specific volume. Then since H equals U plus P times specific volume, this is similar to what we saw for closed systems, but with the internal energy U replaced by the enthalpy H. This automatically takes care of the flow energy, and there's no need to account for it separately using the enthalpy. The energy is simply the mass times this energy per unit mass, or E equals m times theta. So the amount of energy that is transported by a mass of fluid is E mass equals m times the quantity of H plus V squared over 2 plus Gz. Or similarly, for the rate of energy transport, E dot mass, which is multiplied by the mass flow rate, m dot, instead of the mass m. Similar to the analysis in the previous video, some of these quantities may vary over the areas. So the most general form of the energy flows are integrals, which may be simplified based on the scenario. But the most general form is what is seen here. E mass in equals the integral over all incoming masses, mi, of the total energy per unit mass coming in with the fluid, hi plus vi squared over 2 plus gzi. This can also be applied to mass out. Again, usually simplifications involve having constant values across the inlets and outlets, one-dimensional systems, or steady flow, or using average values such as the perpendicular velocity. The first such simplified scenario we're going to see is for steady flow. In this situation, there's no change in any property with respect to time. This applies to the volume, mass, energy, as well as the total boundary work and net influx of mass. Also, the heat and work input remain constants, so what this reduces to is that m dot in equals m dot out, and E dot in equals E dot out. Similar to last week, we can expand these E dots into their various energy contributions, so we get Q dot in plus W dot in equals the sum of all energies coming in, m dot thetas, equals the same thing going out, Q, W, and sum of m dot theta. Going even further, theta can be decomposed into its individual contributions of enthalpy, kinetic energy, and potential energy. Another form of this is to look at all of these values coming in at some point 1 and going out at some point 2, where this becomes this equation down here, where Q is a net heat in per unit mass, W is a net work out using the standard sign convention. Some notes on some of the terms in the previous equation. Again, by the standard sign convention, Q is positive coming in, W is positive going out. Delta H, H2 minus H1, is a change in enthalpy of the fluid. This is usually found either in tables, or for ideal gases, we can use the equation Cp times delta T. In many cases, the change in kinetic energy and or the change in potential energy are either 0 or are small compared to the change in enthalpy, so often these terms can be ignored. We have now reached the end of this video, meaning it is now time for your pre-lecture example. Here it is, along with the answer. If you have any questions on any of this, please bring them to class.